So we are going to kick off. Thank you very much for joining our today's webinar. I'm Anna Barashok, a digital marketing strategist at EPs. I will be moderating this webinar, but we have wonderful speakers today who will now introduce themselves. Just one thing before we move on, Q&A will be at the end of the session. If the question, let's say, is urgent, ping it in the chat. I will write it down and I will ensure that we will not miss it at the end of the session. Yeah, but just be aware that all your questions will be answered at the end of the presentation. So I'm giving the word to Luc.
Hello, everyone. Welcome to this session organized by EPs and also jointly presented by jointly presented with Sodac. Today's theme is energy harvesting for IoT devices from idea to reality. What we had in mind was to give you maybe some overview of what we mean by energy harvesting, but most important was also to give you some real examples and how a customer has been implementing the energy harvesting solution using the EPs components. So that's why we are very pleased also to have Sodac with us presenting to you their latest devices related to the animal tracking system. So maybe just to I'm moving to the next slide, which will be the agenda for today. And Anna, you should give me now the control of the slide. Yeah, it's moving now. So today's agenda will be is shown on your screen. Just a few words, first of all, on the introduction. So this session will be recorded. Okay, and as Anna mentioned, you can submit your questions by the way through the chat section. This will be then this will be even shared afterwards by Anna at the end of this session, and hopefully we'll be able to answer most of them. I will give you a brief overview also of EPs, what we are doing. Then the stage will be on Sarah, who is going to give you some principle of energy harvesting, how to do some power budgeting, and how to make some selections of specific components to address the power budget which has been needed. And then we'll have Jan Willem from Sodac presenting the use case which has been implemented. Maybe just a few words about the speakers before we actually start. I'm the European Sales Director at EPs. I bring more than 25 years of experience in the semiconductor industry with different management roles in sales and marketing, and also some technical responsibilities in ASIC development. Sarah is our Senior Field Application Engineer at EPs, and she handles the technical support. She helps designing the evaluation boards and the demo kits in order to demonstrate also what could be done for using the energy harvesting in electronic design. And she handles the technical training and the webinars around the AEM at EPs. Jan Willem, I just need to move. I want to make sure that the slides are moving. Jan Willem is the CEO and co-founder of Sodac, with his technical background and entrepreneurial spirit. He started the company by offering weather stations across Africa in 2013 and has been a pioneer in the IoT market ever since. His ambition is to find the right balance between sustainability and successful business, which allows Sodac to have a unique position and value proposition. All right, so moving to the next slide. And I'll give you a brief overview of EPs. So first of all, it stands for Electronic Portable Energy Autonomous System. We are a fabless semiconductor company. We were founded in 2014 with more than 30 people. The headquarters is in Belgium. We also have a design center in Switzerland. We have an office in the US, in the West Coast, and recently also we had some sales presence in Asia, especially in Taiwan. We have more than 15 patents.
Luke, can I interrupt you really for seconds? Attendees are asking you to increase the volume of the microphone if it's possible. Yeah.
Okay, so audio settings, microphone. So hopefully it will be. Hopefully it will be better now. So yes, I was saying that we have 15 patents related to low power design techniques and also to some maximum power point tracking system that we will cover later on. In terms of sales channels, we have 12 distributors. Some are worldwide and some others are local distributors. We are focusing on low power design technique, on low power design applications. This is the core business of EPs, and in terms of market segments, we are focusing on smart agriculture, retail business, industry 4.0, some applications also in the automotive. Moving to the next slide. Right. So why energy harvesting? Our main customers are developing IoT type of devices, which are being deployed everywhere now to sense, to measure data, to monitor systems, monitoring health, for instance, or to track goods or valuables. Those devices are now battery powered. More and more often they will be batteryless, or sometimes they will also require some battery replacement, which creates a lot of issues or headaches, as we say, in terms of replacement of those batteries. Some of the devices, for instance, are in very remote locations, not very easy to be reached. So energy harvesting is one of the solutions to address those main issues, and that's the reason why we are having this webinar today to explain to you the main benefits. Okay. Moving to the next slide. So as I said, we are a semiconductor company. And as of today, we are developing what we call a power management IC, that's the one that you see on the left, which handles the energy which has been harvested from the outside world, the ambient energy, and which will store this energy into a storage element, could be a supercap or rechargeable battery. Okay, so this is what we do as of today. Later on, we will also have on the market low power or ultra low power MCU, which will be released in the course of 2021. And one thing that which is key also for EPs is that we're building an ecosystem with different partners to have this type of edge devices, partners developing sensors, for instance, humidity, temperature, whatever. Processing, we cover it with the low power MCU that we have available, and communication. We have customers of ourselves. We have also implemented solutions using radio chips like Bluetooth, low energy, LoRa, Sigfox, and so forth. But as of today, we will be just focusing on the left part, which is the harvesting part. Okay. In terms of market segments, what we see in the energy harvesting world and where we see volume production there, the smart retail business is a key one, especially for electronic shelf labels. Smart agriculture, a perfect example is Sodac that Sarah and Jan Dylan will cover. We see also a big trend for the wearable market, smart connected watches for outdoor watches, for instance, smart industry for asset tracking, and also healthcare for fall detection for elderly people, for instance. Benefits, of course, are like removing the maintenance cost of replacing the batteries. You may also have some features because you can take benefit of the extra energy available, but you may also reduce the storage volume since you can use the ambient energy to supply directly your electronics and reduce the size of the battery, for instance. Or you may also extend, of course, the lifetime of your battery by using the energy harvesting. If we look at some customer examples that we do have at EPs, cattle tracking, for instance, in using the photovoltaic, so that will give us some highlights about that. Asset tracking as well, asset monitoring or predictive maintenance. So are some of the key applications where we see the need of energy harvesting, or the benefit, I would say. And we are also involved in electronic shelf label. Some of our customers, for instance, are using the RF energy harvesting to supply those devices. Okay. And just to finish off on the type of products that we do have, looking at the PMIC, in fact, we have what we call the ambient energy manager family, AEM, and we cover, let's say, 4 types of ambient energies sources. The first one is being a photovoltaic. This is where we see the most interest so far. Actually, we prefer to say photovoltaic than solar, because in fact, we are supporting indoor and outdoor as well, okay? And that will be mostly the focus of today's session. Then we also support thermal using TEG, thermoelectric generators. And in terms of AC sources, we support also vibration or mechanical type of energies, and also RF in the high frequency, like 915, 868 megahertz, or also 2.4 gigahertz. Okay, so those are the products that we are supporting. And next, I will then give the opportunity to Sarah to give you some highlights about the principle of energy harvesting and some use cases. Sarah?
Yes, thank you. Okay, can you hear me well now? Is it better, the sound? So thank you, Luc, for the introduction. What we will now be looking at is a bit how to get the energy harvesting into your device, what you need to make it happening, and how the AEM works. So energy harvesting, as we just described, for different, sorry, the slide are not moving. Yes. Okay, so as we just described, energy harvesting could be used in different markets. It could be used to remove the maintenance cost and logistic and issues you can have because you have to change the battery. It can also enable new features, since you will be getting new energy every day, or when the light is there, when you have a difference of temperature, when you have vibration, you can actually use this energy in a different way than just storing the energy for 5, 6, 7 years of lifetime for your device. But what do you need to actually integrate the energy harvesting? You need first an harvester, which will be transforming the energy into the electrical power we will be dealing with the AEM. So this one could be different type of harvester. So like we mentioned, for the light, indoor or outdoor, it will be a PV cell or solar cell. Actually, the material and the technology will be different, but this is quite the same idea. For the RF signal, we'll be using an antenna. As we mentioned, for difference of temperature, it will be TEG, so thermoelectric generator. And for vibration, movement, or other sources, AC sources, you have different sort of mechanical generator. What you will also need is a storage element, which will actually, it can be a rechargeable battery, but it can also be a supercap. So it's up to you, it's up to the autonomy you would like, and it depends on your design. And directly from the AEM, you can supply your hardware device. Sorry, I cannot get the slide moving. Okay, so if we look, you have the harvester and the AEM in between, you have the storage element. And if we look closer to the AEM, you will first find a boost controller, a boost converter. which will be between the source, so the harvester, and your storage. So being a rechargeable battery, a supercap, or any storage element you would like to use. This boost converter will be working with MPPT tracking. So if you are not familiar with the MPPT tracking, the MPPT tracking, it's actually a way to ensure that you are working at the maximum power point. If we look at a PV cell, which is the famous harvester we all know, if you look at the power versus the voltage, you will have like a curve, like a bell with a maximum power point. The curve will change with the luminosity. So if we take the same PV cell below two different luminosity, you will find two different working voltage for the different luminosity. And the idea is that the AM will adapt the working voltage to be sure that you are always extracting the maximum. If you don't do that, if you are just working at one defined voltage, then you cannot ensure, and you might actually be extracting less power than what you have available. What the AM is doing, it's actually measuring the open circuit voltage, which is called here VOC1, VOC2. So for the two different luminosity, which can change during the day, it's measuring the open circuit. It will apply a ratio, MPP ratio, which is defined by configuration. So this is something you will configure to the AM. It's an information you have to give him so that he can calculate the new VMPP, the new working voltage it should work at to extract the maximum power. So those ratio, it's providing in the harvester datasheet. So this is something you can actually find in PV cell or TEG datasheet or any other harvester. And it's quite important to do so. So like we mentioned, if we don't select the right ratio, let's say you select 90% when actually it should be 75 based on the technology, you are just limiting the AM to extract the maximum power. And like I mentioned, you can find for PV cell, you might find some table with the direct information. So you have the VOC, you have the operating voltage, so you can calculate the MPP ratio. And for the graph, you can find also graph. It depends of the manufacturer, but anyway, you should find this information. And if you have any question, or if you are wondering what's the ratio for one harvester you would like to use, feel free to always come back to us. So we just mentioned the boost converter in between the source and the storage element, but you also have other block in the AM. You have first the cold start circuit, which will allow the system to start alone, so without any external supply or help or anything. So as soon as we have 3 microwatt, 380 millivolt, those are the condition to cold start, the AM will get started. It will make the boost working and will be extracting the energy from the PV cell or the other harvester. You also have an internal buck converter, which is supplying the digital core, so you cannot not actually use it, but you have linear converter that you can use with providing two regulated voltages. So you have HV out and LV out. Actually, you can disable them. You can define, okay, I'm just using HV out at 3.3 to supply my system, or you would like to use the 3.3 from HV out and a 1.8 on LV out to supply MCU. So you can choose to enable, disable. You can also control them. So you can have one always used for MCU, for example, and you can power gate the other. So this is up to you. They are both there as an option. Regarding the storage element, you can protect it from overcharge and over discharge. So you can define a level, protection level with configuration. So you have the CFG, so it's 3-pin, CFG 210 to configure those level, and you have a table in the datasheet to help you define which mode you should be using. We also have a custom mode if you would like to define your own protection level. And if you don't find, or if you have any question, also feel free to contact us. Just about the configuration, everything is made with I/O, so there is no software in the AM. It's purely hardware product. If you would like to start, we have some eval kit that you can find on Moser. You have different eval kit. For example, we can see here one with the SMA connector to connect an antenna. You also have other EVK for the other projects. So Luc mentioned the 10i41, the 20i40, and the 13i40. And you can actually get the AM integrated in your device. And we will see some example based on the cattle tracker Sodac has been designing. So you can see on the video these small elements. If we look inside, what we will find is different blocks. So you have the radio, some GPS, the PV cell used to collect the light and the energy, a rechargeable battery, and in between the PV cell and the rechargeable battery, the AM10i41. And actually how to select the PV cell, how to select and size the rechargeable battery, we recommend to base the choice of those elements on energy balance. So the idea is to start from the load consumption. So for example, if we took an hypothesis of 1 milliwatt at 3.3. So it's just an hypothesis. We can look at the energy consumed over a day, because every day the light is coming back, but we could do this small exercise over a week, a month, a year. So here over a day, we estimate the load consumption. We integrate the different losses. So since we will be using here the internal LDO, we integrate the LDO efficiency, the internal losses of the AM, and we integrate the boost efficiency, which will be around 90% since we will have more than 1.5 volt at the input. So we can look on the data sheet of the AM, you have the boost efficiency curve like you can see here. And actually, if we also integrate the fact that we will have 10 hours of light, we can change it, but it's an hypothesis. We can estimate that we are looking for 3 milliwatt from the source, from the PV cell. So this could help us to actually look at the PV cell datasheet and start selecting the one we will be using. And about the storage elements, since we know that over 24 hours, we are looking to, we will be consuming 97.2 joule. So with all the losses integrated, and we would like 40 hours of autonomy, because during 10 hours we will be getting the energy from the light. The rest of the day, the 14 hours left in the day, we will be using the storage element as the source. Then we are looking, we are trying to store 56.7 joule. And as soon as we have those details, we can actually start looking at the different rechargeable battery data sheet or PV cell. For example, we know we are looking for 3 milliwatt. We can start looking at one axis. This one is, we made some measurement, but you can also find that kind of graph information in their data sheet. So we can see that below 10,000 lux, they are providing 7 milliwatts. So this is more than what we are looking for. So it will be enough to use this PV cell. And for the rechargeable element, we can estimate that we are looking for 4.2 milliamp per hour, so just for the 14 hours of autonomy, and we can start looking at different options. Here you can see that it starts at 16 milliamp per hour, so it will be far enough, and this is one option we could be using. Another example is our demo kit, so this one here, that it's actually based on, I'm trying to get back, okay. Sorry. Okay, there. So I hope it will stay there. So you have the PV cell. No, okay. You have it's okay, we can stay there. So you have the PV cell. It's a 3G solar PV cell integrated for indoor light. So DSC technology there. You have the AM10i41 inside that you can see here on the PCB. Okay. I will try to stay on the slide. You have the AM, you have some sensor that you can actually see in my video. You have the supercap inside. We are actually using Capix supercap, and everything is integrated in the datasheet. You can also see the BLE IC we are using with the antenna, and we have a BLE communication that we can see. For example, I put this on the phone here, and you can see the data that are coming from this one. And I don't know why I cannot see this slide anymore, but you can see supercap charging up, staying alive and at the maximum during the day, and getting down because it's actually supplying the electronic during the time there is no light. So that was it. And if you have any further questions, feel free to contact us. And Jan, this is your turn.
All right, Sarah, thank you very much for the introduction. Of course, you've covered a lot of the things that were for Sodac the reasons to choose for this EP's solution. So let me see. I've requested control, so I can go to the next slide. Yes, can I? Is it? There we are. So my name is Jan Willem Smeek, and I'm from the company Sodac. Sodac is a company from the Netherlands. We have been in the playing field of IoT for many years, and we are a very happy customer of the EP's AAM 10941. Let me see. Can I go to the next slide? What I want to talk about today is about a short introduction about Sodac, about IoT and the challenges we have in terms of sustainability, how at Sodac we are solving this, and as a use case, I'm going to talk about the movement project. Movement with the OO in there is, or the MOO in there is the company that actually makes this trackers for the cows. Let me see, can I jump to the next slide? So Sodac is a company that was founded some 7 years ago. We have 37 staff at the moment, and we've been active in IoT products and delivering our goods and products in 55 different countries so far, and we've served more than 2,000 clients with our products. The hardware that we've been produced has gone in the numbers of well over 50,000 units, and we've been working on more than 180 different IoT projects since we have started. So we see ourselves often as the extension of IoT departments of large companies. They hire us for that purpose, and then we jointly develop products, intellectual property. We make hardware and the embedded software that runs on the hardware. We do have quite a few off-the-shelf products that we are selling through our web shop. And of course, for a lot of these large companies, we start off with a proof of concept, and then via a prototyping stage, we finally get to a final product. So this is typically the way that we work as a company. So it's not just the standard products that you find in our web shop, but also a lot of projects and opportunities that we had with all sorts of different companies. Now, since we started in IoT some 7 years ago, the market for IoT has grown tremendously. The chart that we are displaying here comes actually from the Gartner Group, in which they explain how we've grown from IT and computing in its simplest form to an enormous market whereby everything gets connected. The whole idea of the Internet of Things is that literally everything around us will be connected. We're talking about tens of billions of devices already, and this is only growing to 50 billion, over 100 billion. It's actually unbelievable how great this market is eventually going to be. Now, the big question that we always asked from the beginning is like, how are we going to power these things? Will all these IoT devices be battery powered? Because you cannot plug them into a wall socket. We don't have mains power in all these locations. So you need for these devices to be autonomous. And if you have an autonomous device, well, you need some sort of a power source. But what happens if all of these devices would be battery powered? If we have a simple AA, a penlight battery, and we look at how much does that represent in a volume, one AA battery has a volume of 8,000 cubic millimeters. We're using the millimeters here for the easier calculation. If we assume that we have 100 billion IoT devices, each using one AA battery per year, we're talking about 800,000 cubic meters of battery waste annually. Now, if you compare that to something more comprehensible, an Olympic swimming pool has a volume of 2,500 cubic meter. So that means that if we really are going to be using AA batteries in all of these devices, we will end up with 300 Olympic swimming pools full of battery years waste every year. Now, that is a lot of batteries. It is unbelievable. You can imagine that even the natural resources are not available to produce that large number of batteries. And at least we don't want to be in a market whereby we will be regarded as such great polluters. So we have to come up with an alternative. The idea, when you start making an IoT device, the first thing you should do is you reduce the actual power that is needed. I'm not sure why I'm going to the next sheet, because that is not the intention. Let me try to go back to the previous slides. Yep. The idea, if you develop an IoT device, is that the first step is that you make it use as little power as possible. Because if you reduce the power to the absolute minimum, it means that you can quite easily start implementing solar energy harvesting. If you have a device that, for starters, already uses a lot of power, forget about energy harvesting. It's not possible. We cannot have a Raspberry Pi, for instance, that uses 2 watts continuously, powered by a tiny little solar panel. It's simply not possible. So you have, as an engineer, you have to go back to your starting point and say, we use as little as power as possible for our device. And what we always say, we use the Sodac power principle, which is sleep when you can, only work when you have to, and keep your communication as briefly as possible. So in the little chart that you see here, you see that the sleep power consumption is next to 0. We only use typically a few microamps in sleep. And then the device wakes up, does something, only for a few seconds, and go back to sleep. If we can make a device that only wakes up, let's say, every hour to do a little bit of work and send that data over the internet, we have something that uses very little energy. And if it uses very little energy, that's where the energy harvesting comes in. Then we can start looking at solar power devices, or devices powered by kinetic energy, heat energy, vibration, etc. So start with the power principle, make something that is efficient, and from there, carry on. Now, I should go to my next slide here. Don't see much happening here. So the challenge that we had when we first started talking to our client Movement is Movement came to us and said, we want to track cows, and then particularly cows that are wandering around freely. The initial market was Australia. So we're talking about farms that are the sizes of 5 by 5 or 10 by 10 kilometers. We want to find our cows there. But the requirements they said the tracker for the cow should fit in the ear of the cow. So the weight limitation was it could only weigh 30 grams. It shouldn't be any larger than 55 by 75 millimeters, but still they would like to send 48 position updates per day. So every half an hour, the cows should tell the system where it is. And the thing had to work for 5 years. Now, how can we make such a device? We straight away came up with the idea that we would be using a small solar panel, but within the size limitations that we had, we worked out that we would only have a space of about 10 by 40 millimeters for a solar panel. And yeah, to make a device that meets these strict requirements, we really had to look in the optimal efficiency for our energy harvesting. I don't see my screen controls anymore. Maybe somebody can assist me to go to the next slide. There we are. So we had to do it with solar. And why did we have to do it with solar? Well, it's good to throw in a little bit of a calculation. The little tiny solar panel that we talked about of 10 by 40 millimeters still produces in bright sunlight a power of about 0.2 watts. Now, if you make a device that is exposed by the sun for about 5 hours a day, you are creating about 1 watt-hour of energy per day. Or if we look at the total lifespan of the device, it means that we would generate more than 1,800 watt-hours in the 5 years, or about 6.5 million joule of energy generated by such a solar panel. Now, the equivalent of the amount of energy that we are generating there is about 580 AA batteries. So with a tiny little solar panel like this, over 5 years, you can generate the equivalent of 580 batteries. So if you're making a device that is battery powered, in this case, you would have to replace the battery twice a week. And we make something that only weighs 30 grams, and that does the same. Imagine the cow has to carry 580 batteries with him. It will be a massive battery pack somewhere on the back of the cow. Well, that would make nobody happy, I suppose. Yeah, next slide, please. So the AEM 10941 is an energy harvesting device that did for us exactly what we needed in this device. One of the points that we have is that if you look at a normal solar plant, like what you see in the picture here, all the solar panels are all aiming in the right direction. But if you have an ear tag that sits in the ear of a cow, you don't have control in which direction it's pointing. So you don't know what the actual output is that the solar panel will deliver. So you need to have something smarter on board that harvests the energy, even if the cow is standing in the shadow. Even if there is very little light, we still want to use all the light that we have to benefit and to make the device work. We harvest the energy that we have. We have a very small solar panel, and still we have accomplished what we wanted to accomplish, is that we have a device that will work 5 years and still deliver the 48 messages that we wanted to deliver. How did we do this? Well, we have this little solar panel that you see in the picture of about 10 by 40 millimeters. In fact, it is 4 X's batteries that we put in a grid. And we have the ePeast energy harvesting chip to manage the charge control here. The software that we made for this device makes sure that it's in deep sleep basically all the time. Only roughly once a minute it wakes up to see if there's any scheduled task for the device. And it will only execute these tasks if there is sufficient power available. We have a tiny little battery on board that we charge to do these tasks. And so one of the methods that we've used here is that we've defined the different tasks that the device should take care of into different categories. So we have low power tasks, like monitoring the onboard accelerometer to see what kind of motion the animal is having. Is it grazing? Is it walking? Is it sleeping? Did it jump a fence? That uses very little energy. So those are tasks that we can do without major impact. But the actual GPS position and the sending of the data takes much more energy. So every time the device wakes up, it sees what scheduled tasks do I have available, and do I have the energy to accomplish this? If the device doesn't have the energy, it will simply continue energy harvesting a bit longer until it has sufficient energy to take care of that task. So it could happen that, let's say, during the night, we will have less frequent GPS fixes than we have during the day, simply because we don't have enough energy. But as soon as the device gets exposed by the light, it will pick up a task and it will continue doing what it is supposed to do. So as a result, we've made a device, as you see in the picture now. This is the latest generation. We no longer use the 2 pins to connect it to the ear, but just 1 pin. to make it even lighter and more flexible. The result is that indeed the kettle that are fitted with this device will send their live GPS data on average 48 times a day. It will send instant notifications if something is happening, like the animal jumped the fence, or if there is other motion behavior that needs to be detected. It communicates over the LoRa network. This is something that I didn't mention. LoRa is a communication technology that we can freely deploy in areas where there's no other LoRa connectivity or no other connectivity available. We simply place a LoRa outdoor gateway on the roof of the farm, and then it will cover basically the whole farm area. It's up to about 5 kilometers away from the farm. And these gateways that we typically use are for a company in Switzerland called Wi-Fix. The Wi-Fix LoRa 1 is what we are using. What you can say is that the area that such a gateway covers is something like 25 square kilometers. Typically, a farmer can have up to about 4,000 cows in such an area. If farms are bigger than that, so if the space that the farm is covering, then we simply put up more gateways. So if the farm is 100 square kilometers, we might put up 4 gateways, and this all works perfectly with this LoRix gateways and the LoRa technology. So basically, this is it for now. There's a couple of questions that came in. Should I be answering the questions that came in for this product? Shall I start this, or what shall we do, guys?
I will. Thanks, Jan. Thanks so much for the presentation. I will take over from here,
Okay.
and I will go through all the questions addressed to Luke, Sarah, and you, and we will start right now. Just give me a moment. So while we are answering your questions, we will just display the contact information, so you will be able to save it if you want to contact us. And yeah, let's kick off Q&A session. So there is something from Thomas Westenberg. I don't think it's a question, it's just a comment. Thomas says, an important feature is the IEM 10941's ability to cope with excessively high solar cell voltages. If you choose a solar cell that generates sufficiently high voltages, even in poor conditions, so for example, clouds, winter, etc., this solar cell can generate high voltage when there is a high level of light. For example, summer and sun. Other manufacturers then overload the supercap. Yeah, thanks for this comment, Thomas. That's really pleasant to hear that. Craig says we are a biotech, personal and military use product in the field. So this is not a question, but Craig, if you have any questions, do definitely reach out to EPs or to Sodac. Question from Thomas Westenberg. Would be interesting to know which LiPo battery, LiPo battery was selected. Most devices have too high IQ. Can anyone answer that?
Yeah, so I can answer this question. We are using a tiny little, simply ordinary lithium polymer battery. The battery is really small, but it's enough to, let's say, deliver the capacity to have an autonomous runtime of something like a week or so. We assume that these animals are in the sun all the time, so the battery is merely a buffer. Now, what we would love to do is move away from using a battery completely. In the presentation of Sarah, you saw a very nice flat supercap that is being used in other scenarios. The problem is that at the moment, the price of these supercapacitors is way too high in comparison to the LiPo. So for us, it is the only possible scenario to be cost effective at the moment but we definitely would like to move to a supercapacitor for not having all the disadvantages that the LiPo battery has. Having said that, normally LiPo batteries, the lifespan is based on the number of charge cycles. If you go into the specs of a battery manufacturer, you see that they specify these batteries for instance, for 300 or 500 charge cycles. So you would imagine that if you make it last for 5 years, you would exceed that number of charge cycles. But in reality, this is not the case. The charge cycles, as are being described by the LiPo manufacturing, are for the complete deep discharge of the battery and then a full recharge again. What we are using is only a rather shallow discharge. So we charge the battery, and then because most of the time we have energy that we're harvesting, we never completely discharge the battery, but always stay in the top end of its capacity. And that means that it will last way longer than the expected lifetime that you would get from the number of charge cycles. So in our case, the very small LiPo battery that we are using is lasting the full 5 years that we have. But we're really dying to get a device working with a low-cost supercap so that we no longer have to deal with batteries.
Great. There is another question to Jan. Are you planning, is from Jerome, are you planning to include other sensors as well in the future?
Now, basically, the other sensor that we have on board is an accelerometer. And an accelerometer, of course, is a wonderful device because it can tell you a lot about the animal, about the behavior of the animal, the moving of the animal. We don't just do this for cattle. We are in a very close collaboration with Wageningen University here in the Netherlands for wildlife tracking. And so one of the things that we do with this accelerometer is we detect anomalies in the behavior of the animals. And in that way, we can use the animal to tell us whether there is poachers in the neighborhood. So you can say if the behavior that we deduce from the accelerometer is totally different from what we normally see, and we see the similar behavior by other animals as well at the same time, well, there is something really fishy going on, and then we can send a patrol to see if there is any poachers around. So the accelerometer is a wonderful tool that can tell us a lot about not just the behavior of cows, but all sorts of animals. And what you're looking at is when is the animal grazing, when is the animal moving rapidly, when is it going to another pasture, but maybe the grass is all eaten up to a level whereby you can possibly detect whether the animal is pregnant, etc.
Great. I hope it answers your question. I shift to the questions to Sarah, and then we will come back to Jan again. Sarah, there is a question from Duncan. Duncan is asking to give the names of the solar cells, and the supercap manufacturers again.
Sarah, you are muted. Sarah, you are muted.
You can also contact us directly if you have a project. We can help you to find other PV cell. The one we have been using here, it's 3G Solar, and the one that has been used by Sodac is Xis. But one is for indoor, outdoor, and there are also other manufacturers. Those are the one we are showing there. For the supercap, we are mostly working now with Capix, but there are also other manufacturers. So I would say the best is if you have a project, maybe contact us and we can see with you what's the best on the PV cell or the other harvester and the storage.
Perfect. The next question is from Brian. Sarah, merci for wonderful products. Thank you, Brian. So Brian is wondering if you have had a chance to try them with the new hybrid supercapacitors, reportedly 6x energy density of supercaps and higher working voltage. And then he brings an example with the link. Yeah, that I can't spell for now.
Brian, if you can contact us directly, it would be the best to discuss, and we can look at the product and test it with the AM. Could be one good partnership.
Good. Next question is from someone anonymous. You only try to harvest energy with solar cells, or did you also try to harvest other sources of energy for your projects?
So I can propose you to go on the LinkedIn page on EPIS. We have other demo that has been shown last year at Embedded World. We have different demo and other demo working with TG vibration. You can also look at our website. We have a demo working with a magnetic core from TCT. So now we are working with other sources. It's just that the light and it's the easiest and the most famous. So that was the first one, but we have the other project working with all the other sources. RF, we have some demo also. So feel free again to look and contact us if you would like the link.
Perfect. The next question is from Bilal. Which BLE IC are you using?
I won't say the name here because it's not really interesting and it's not the best on the market. So I would say that we could be using any BLE IC already, as Ian mentioned. It could be LoRa, it could be 6FOC, it could be other radio. It's just here an example of what you can do, what you can supply, and BLE is the easiest to show you and show you real data. But feel free also to contact us if you would like to discuss the name and the demo schematic.
Right. There is a question from Ibra. He's asking, is the product regulated, FCC, European, Australia?
Is that a question to Jan Willem, I guess? Or is it?
I actually don't know. Yeah, it's not addressed.
If it is related to a product presented by Sarah, it's not a product that we sell to customers. So it's a demo kit. So we don't need the CE certification or FCC whatever for this type of certification, since it is a demo kit. Now for the real product, maybe I'll let Jan Willem answer.
Yeah, so our products are typically certified by the local regulation authorities. So depending on the markets where we are operating in, so in Europe we CE certify them. In Australia we go through the local regulators.
Good. So we have another question from Ibra. I think it's a great question, and it's addressed to Sodac. He's asking if Sodac tried other suppliers of harvesters, and what is the comparison with IM 10941? How is it better?
Yeah, well, of course we investigated the market on what was available. We were working in this field even before the AEM 10941 came out, and we found that the combination of features that the AEM 10941 had wasn't available at that time by any of the other manufacturers, and that's why we chose it, and we are really happy about it.
Okay, so the next question is from Stefan. Have you actual solutions working for licensed spectrum LPWN, in brackets NB-IoT, LTE M1, sorry, or upcoming 5G and R that have higher power requirements than LoRa or other unlicensed spectrum LPWN?
Yeah, so Sodac has a range of products in the narrowband IoT and LTE-M sphere. We've been working with these technologies for quite a few years now, doing some really large projects. And early next year, January, February, we will be launching a new board that has the energy harvesting module on board, supporting narrowband IoT and LTE-M. So stay tuned. January, February, we will launch these new products.
I can maybe also comment that I saw different question about that. So yes, we can actually supply other radio protocol than LoRa or BLE. It could be NB-IoT. It's actually, it depends on the energy balance you can have. It depends on the environment you will be working with and how much energy you can get. if you are consuming a lot for sending a message like with LTE or with NB-IoT, you can just play with the frequency you are sending messages, and everything is about finding the balance to get enough from your environment. Well, the balance between what you are consuming, what you are getting from the environment, and this is what it's really important. And this is why in the example I'm starting from the load consumption. So having an idea what you want to supply, and from there we choose the right harvester and the right storage. This is really the idea. Of course, if you are consuming too much, like I don't know, a smartphone or something like that, you will need a big super cap or big storage or big PV cell. So this is where we have to balance and make the right choices to make your system autonomous and working with only energy harvesting. Or you could also have the primary battery option. I didn't mention it, but it's an option to have a primary battery, so a non-recharge element that we use as a backup. So there are different options we can look at, and if you have a real case, feel free also to contact us and discuss the number and the option.
Great, thanks, Sarah. There is a question from Prajna Jit. I hope I pronounce your name well. What mechanism you have followed to maintain the quality of service of your system? Because solar energy is not that consistent, so there is no guarantee that adequate amount of energy can be harvested. Good question. Thanks for the question.
Yeah, so in my presentation, I already mentioned it briefly, that what we do is before we undertake a certain task in the device, we see if the battery level is actually high enough to be able to accomplish this. So if, for instance, we don't have enough energy in our energy buffer to do a GPS fix, we will send still a LoRa message, because the LoRa message only takes a fraction of what it takes to get a proper GPS fix, telling the backend system, listen, we're still alive, we're still working, we can still tell you about the animal behavior because of what we're monitoring from the accelerometer, but we don't have a GPS fix yet. We will send one as soon as we have enough energy again. So we control whatever we can do with the available energy that we have. And in the meantime, we continue harvesting, and sooner or later, we will have enough energy again to do what we are supposed to do.
I hope that answers your question. The next question is from China. For an application in an agricultural field to supply own sensors, would it be more ingenious to use solar or vibratory energy, or a combination exists maybe? Thank you for the nice presentation.
So about the combination, I also saw other questions. So we can combine different source of energy. You can actually put everything in one storage element. So it could be, you could use different sources. This is not an issue. For the question about smart agriculture, I would say that it depends on the available area you can allow you to use for the PV cell, because with vibration, you will have to use a mechanical harvester, see when the vibration is there and what kind of harvester to use. For the PV cell, you will have to use some area. So it depends a bit on the mechanical constraint you have, the source of vibration you are using. I would say that the light is the easiest. This is where you will find most, I would say, more different option for the PV cell, but we can have a look, and it always depends on the environment. So there is no one answer that I can give you there.
Great. The next question is from Leonardo from Brazil. Hello all, congratulations for the very interesting project. I'm from an automotive segment from Brazil. I would like to know if there is some application or solution for this business niche. I don't know, Sarah, maybe you can talk about Smart Jack. So this is the application that uses our IAM.
Or maybe if I may comment, maybe if I just may comment.
Sure, go ahead. But maybe try to Luke. Maybe try to remove the headphones and see if the sound is better. Because
yes, can you hear me now better now?
Not really. Can you remove them like completely? and
Is
see
it okay
the-
now?
Yeah, try it now.
Is it okay?
Well, it's the same, but go ahead.
Yeah. Sorry about the sound quality. Just to answer about the automotive, yes, we are partnering with one of the world leaders in the glass industry. It's public, so we can mention that it's on our website. So it's called AGC, and they did develop this jack device, which is a system that you stick on the windscreen, which is there to detect some cracks on your windscreen, for example. So this is for predictive maintenance. We did also partner with some companies developing some sensor for to monitor the tire conditions, also the pressure of your tire. So those are some of the examples in the automotive application.
Right. Yeah, Leonardo, if you need more examples, you can also reach out to us and we can share more information with you on the applications that we already work with. Philip is asking, how the GPS stay alive, hot in brackets, to not take a long time to synchronize?
Yeah, that's a good question. Indeed, what we do is the GPS module that we are using in the current version of the kettle tracker is the u-blox EVA M8M. This one can be kept in a hot start mode by supplying just a few microamps of current. So basically, while it is in the hot mode, it preserves things like the almanac and the ephemeris, so that the next fix is way shorter than a normal cold fix. So what we see is on average that our GPS fixes are averaging under 10 seconds per time that we do a GPS fix over the whole lifespan of the device.
Great. The next question is from Francois. Do any of the PCB manufacturers stock the IM10941 as a standard component? I would like to integrate them into a self-designed sense and control circuit and have this made all surface mount in tens or hundreds per order.
So they don't really stock, but you have the component available on Moser, and you can just buy the component and make it mounted. So this is what we do for the eval kit. So yeah, you can you can find where to buy the AM on Moser. It will be the easiest, I think.
Yeah, by the way, and if you're implementing our solutions, don't forget also to reach out to us and announce about that, so we could bring it forward on our website and on our social networks as well, so it can also increase your visibility. We have quite some questions still, so stay tuned, don't leave. There is a question from Praj Najit, once again. In a batteryless system, if a battery or a supercapacitor is used, then how the system is called as batteryless system, because in any way someday we have to replace a rechargeable battery. What should be the precise definition of batteryless system?
You can maybe look at it as autonomous system. It's you don't have to change. Well, the rechargeable battery might have to change after the lifetime, which could be 6, 7, 8 years. Supercap, they can go up to 15 years. So let's mostly call it an autonomous system where you don't have to care about the status of your battery, and it's autonomous, in energy. You don't need to worry about it.
Great. The question from Stefan, what are typical power density levels for different type of harvesters? Solar, vibration, RF. What about the max power of such harvesters?
So it's really a difficult question, since it really depends on on the harvester, on the environment. Most of those details are provided in the harvester datasheet. So I would say that the best, if you are looking for that, is maybe to contact us directly so we can have a look at your environment and give you some details. The maximum, I can tell you that the maximum we can handle is 110 milliamps at 5 volt. This is what we can handle at the input. And most of the time, the power you are getting from the source depends if you are in indoor environment with just office light, or if you are near a window, or if you are outdoor. For the vibration, it depends if you are working with a small acceleration or high peak acceleration. For TG, depends of the difference of temperature, depends of the size and the area you will use, so TG. So it's really complicated to provide you one answer. We can provide you IDs based on your environment and give you the right contact for the harvester. So I would say the best is contact us directly.
Great. The question from Hilko, the HV of the IEM 10941 supplies maximum 80 MA current. The inrush currents of GPS modules can exceed these currents. How has this been solved with Sodac?
Yeah, so I mentioned already that in the current version of the device, we use the EVA M8M GPS module by u-blox. This one is rated for a maximum current, the IMAX, to be 67 milliamps. So that's well within these limits. And this also, let's say, aligns a bit with the question that Richard Battle asked about what is the maximum TX current for the LoRa communication. That is in the range of about 50 milliamps. So both the LoRa communication and the GPS fit within what the AEM 10941 can supply.
And maybe I can just comment, if you are really if you need higher current, like for Wi-Fi communication, we already saw it. You can just disable the LDO. You don't use it. You use the boost converter with the MPPT function, the cold start, and the storage element, and you can use an external DC-DC from your storage. So it could be something you already have because you have the battery, and you can just plug the energy harvesting to your storage element, which has to be now rechargeable. But I mean, you are it's not you don't have to use the LDO. It's something you can use. You have well-regulated voltage if you want to use and supply directly, but you can also disable them.
Thanks, Sarah. There is a question from Richard. When using supercaps, the leakage is quite an issue, right? Would you use a keep alive cell in this type of application?
So the supercap, the leakage, actually, it could be integrated in the estimation when choosing the size of the harvester. So it could be seen as an internal consumption of the system. Of course, if you have a big leakage, you will have to compensate with the harvester. So maybe it can be some issue on the system because it's consuming too much. So it's something you have to look at it. But with the CAPEX, we have 1 microamp per farad leakage current, and it's nice, and it's integrated in the energy balance. So the PV cell we are using here, it compensates the leakage of the supercap.
Perfect. I hope it answers your questions, Richard. There is a question from Craig. Can an external jack be engineered into integrate into our mobile light medical device? Yeah, I'm not sure what the device is about, mobile light medical device.
Yeah, of course, like in any type of connector could be integrated in any device that you're making. So we at Sodac, we make devices that, for instance, have a waterproof USB connector to connect it to the outside world. Typically, in the case of the cow tracker, the first generation had what we call pogo pins that were exposed to the outside of the enclosure. So we had some sort of a docking station made that you can connect the device via still a very waterproof connection in this case, a docking station. So yes, it can be engineered so that you have external access to your device.
Great. What about the overall price? That's a question from Dennis. What about the overall price of this Sodac solution, which I guess is an important factor to be accepted by the market?
Yeah, what you see is, of course, people are always looking for the cheapest possible solution for the problem that they have. So what you should look into is what we are trying to do is we for a farmer, we are trying to protect his cow. That is the business case that you have. So you need to look into each business case that you have is what is the percentage of the value of the object that you want to protect, the percentage that you want to pay for the device that is doing this. So if we are looking at a cow that in some places around the world may have a value of, let's say, $900, and if the owner of the cow is willing to prepare 3% of the value of the animal for protecting it, you know that the budget you have to develop such a device is $27. So that's always the fine balance that you need to find. Now, in any form of electronic design and development, the larger the volumes, the lower the price. So you need to work on a business case that is, one, looking at what is the customer prepared to pay, and two, what is the volume of the market, and there somewhere in the middle you find the target price of the object that you need to make.
Yeah, and also the consumers are starting to shift in terms of what kind of products they consume and how long they last and what kind of effect they have on the planet. So this is also very important to consider. No. There is a question from David. Is your setup size of solar panel plus EPs sufficient to support cellular technologies instead of LoRa? So for example, NB IoT or Cat M1.
Yes, so that's why we mentioned a bit earlier. So it could be used for other radio protocol. It's about the energy balance, and there is no limitation. The limitation will be what energy can you get from your environment, what mechanical constraint do you have on the harvester, and that kind of details. And from there, see what you have as energy and what you could be supplying, how often could you be sending messages. But for example, we already saw demo with the Wi-Fi communication. It's just that you cannot send a message each 10 seconds, like BLE. It's about that.
What we normally use as a rule of thumb is that to send a narrowband IoT message takes approximately 10 times the energy of sending a LoRa message. So in our case, we now send 48 messages using LoRa per day. So the same device could probably send 5 narrowband IoT messages a day without much of a change in the setup.
Thanks, guys. The next question is from JL. Does EPs have any combined energy harvesters? One that could, for example, harvest energy from PV and piezo?
So actually, we made a webinar with our rep Chip Select about that, about combining multiple sources. The thing is that you could do with one AEM if you want, but it means adding some switch to control which harvester will be connected, when to use it, which one will be used for the cold start. So it's a lot of trouble and issue. What we recommend is to use one AEM configured for your harvester with the right MPPT. And as I mentioned in the presentation, if you don't use the right MPPT, you are just not allowing yourself to extract the maximum. So you are just putting some limits on the energy harvesting, and we know that it's low power. So I would say that the best is really to, for each source, use one AEM with the right configuration and connect it to the same storage. And that way you can harvest from different sources with the optimization on each sources.
Great. And by the way, the webinar that Sarah has mentioned with Power Film, it's available by demand. So if you want to request it, we can send it to you. So write to support@eps.com and we will send it to you. The next question is from Richard. Jan, what's the TX current during LoRa communication? Are you taking the power directly from the energy storage, as I believe the LDO doesn't have enough power?
Yeah, so I already mentioned this one, is that the maximum current we have to transmit a LoRa message is in the range of 50 milliamps. So this would work if you have to deliver a higher current, then indeed you should pull it from your energy source directly. It's good that in the previous question we mentioned narrowband IoT and LTE-M. With narrowband IoT, we can have current peaks that are 10 times higher. So you could have 500 milliamp peaks in your transmission, and then you should definitely look into pulling that from your energy buffer directly. So either your supercap or your lithium battery that you have on board.
Perfect. Thank you so much, Jan. I think we ran out of questions. Thank you so much for being with us today. If you have any remaining questions that are left, you can see, I hope you can see the slide with all our contact information from Sodac and from EPs. We will be happy to hear from you and help you to find a way to make your device energy autonomous. Thank you so much.
Okay, thanks. And also on behalf of EPs, I'd like also to thank Jan Willem for his presentation and for his support to show a real use case. Thanks. So thanks for that. Great. Thanks everyone also for attending this session, and hope it has been useful to you.
Great. Thanks for having me, guys.
Bye.
Thank you. Take care. Thanks everyone.
Bye everyone.
Thank you. Thanks. Bye-bye.